next steps. We're excited for the steps that come after this as well, traveling around the world on a Bonderman Fellowship. So I'm really excited for Jack, and he's done amazing things in the group and gracefully handled sort of shifting funding landscapes. And so it has been thus far a pleasure, and let's hear what Jack has to say about it. Okay.
Cool. Thank you so much. All right, with that, I'll go ahead and get started on my talk today, which I've titled Earth Abundant Thin Film Devices for Photovoltaic and Electrochemical Applications. And before I jump into the meat of my talk and talk about the technological developments I've been working on, I want to go back and talk about some technological innovations from the 20th century. This is the Ford Model T, which was manufactured in 1908, and it was an amazing invention in that it rapidly increased the amount of vehicles that in the United States per person, on a per person basis. This vehicle spawned a lot of manufacturing, and it currently holds the record as the 8th most manufactured vehicle of all time. And it led to this rapid increase up to about 1 vehicle per person. Around the same time, 20 years later or so, in 1928, penicillin was developed. And over the next 100 years or so, 80, 90 years, there have been all of these antibiotic developments over time. So both of these things, the development of cars and the development of antibiotics, have been massively good for society. This has led to a lot of economic development and saved countless lives, but it's also come at some costs as well, as many technologies have. There are pros and cons to these. Of course, people should know about the impacts of fossil fuel usage and how it affects the warming of the planet. This rapid increase in cars and all other forms of burning fossil fuels has increased rapidly, and this has led to a warming of the planet due to increased carbon dioxide in the atmosphere. And this has led to a rising of the sea levels, among other negative effects from climate change. And they're projected by the end of the century that sea level rise could be as much as 10 more feet. It's only been 10 inches so far since the start of the 20th century. But even with 3 feet of sea level rise, looking at a map of Charleston, South Carolina, close to where I'm from, you can see that maps are going to look completely different. And in places like Charleston and New York City, where there's money to put up seawalls, okay, this isn't as, this maybe can be ameliorated, but places like Mumbai or places that are poor, it's really going to have a lot of drastic effects, and there's going to be climate refugees from around the world. And so you can see all of these places that are at risk. It's roughly $35 trillion and millions of people that are at risk due to this changing climate. So this is something we really need to address. Additionally, the rise of pharmaceuticals has had this unintended impact as well. Pharmaceuticals have increased to nearly 1,000 prescriptions per 1,000 people. So there's pharmaceuticals are widely used, particularly antibiotics. And this has led to the rise of antibiotic-resistant bacteria. This is on the rise for multiple classes of bacteria. Additionally, these bacteria, they go into, they're excreted by humans in their waste, and this goes to wastewater treatment facilities that currently aren't designed to break down these pharmaceuticals, antibiotics in particular, because that's exactly what they're designed to do, is to not be broken down, is to actually destroy microorganisms. So pharmaceuticals have had this rise over time, and there's, in addition to antibiotics, there's other examples where fluoxetine has led to shrimp moving towards light and exposing them to predation. Metformin and salmon here in the Puget Sound, which is actually reducing the reproduction rates of these fish and causing intersex fish. So there's all these negative impacts. And even if you're a vegetarian and you don't really like sea life, it's a problem for you too, because it's in the drinking water. All of these red dots represent measurable concentrations of pharmaceuticals in the drinking water. Now, there's currently no known associations with these low-dose concentrations over time, but we're certainly exposing ourselves to risks, and it's only going to grow as we develop more pharmaceuticals. So what can we do about this? Well, I've kind of framed this as making devices to solve these problems. Just thinking back to our chemie fundamentals, you can think about it in terms of 2 black boxes here that we want to develop. A black box, or a device that turns sunlight into clean energy, or pharmaceutical contaminated water into clean water. And so how can we make these devices? Well, we want them to be inexpensive, scalable, and reliable, just like the Ford Model T. right? To make an impact on the market, it needs to be able to scale up and really massively grow if we're actually going to address these world-sized problems. And so how can we do this? Well, one strategy is, and towards the inexpensive and scalable aspect, is to use Earth-abundant constituents. This is a plot of the how abundant an element is in the Earth's crust on a log scale for different atomic numbers here. And so we want to be using elements up here like copper and zinc or silicon, and not things like tellurium or palladium. Additionally, I work with a class of devices called thin films, which represents this size range here between 10 nanometers and 5 microns. And so it's not very much material for these devices, but we can do a lot of interesting electrochemistry and photovoltaic applications with these thin films. Additionally, these thin films are amenable to roll-to-roll processing, where you can scale them up in the same way you would scale up manufacturing newspapers or something like that. So these are scalable processes that we're using Earth-abundant constituents. So with that, I want to quickly outline my talk and talk about what I've been working on for the past 5.75 years. In the first part of my talk, I'm going to talk about my photovoltaic work, give a brief introduction to photovoltaics, talk about 2 different papers that I've published. Additionally, I'm also going to give a brief introduction to electrochemistry and this pharmaceutical degradation ideas with electrochemistry, and then a paper that we have in preparation. So starting off with a little more background about PV. Currently, or it was the case not too long ago, that utility scale PV was way too expensive to be competitive with existing electricity generation technologies. This is a plot that shows price in relation to parity. So red is bad. It means PV is way more expensive than the local electricity. And you can see this was the case just in 2012. But over the course of my PhD, there's been a massive change in the price of PV. It's fallen so much to the point where in almost every state, it's better to have PV. So, yeah.
High five.
This is a really good thing. Yeah, this is a really, it's the good news and the bad news. This is really good news, right? We're seeing the proliferation of PV in a way that it's getting cheap to the point where it can beat out existing technologies. But this raises the bar for research, next generation PV technologies to compete with this 60, 70-year-old process that is silicon PV manufacturing. So here I've given a brief overview of different PV absorber technologies and also their solution processed record device. So this is power conversion efficiency here, and this is the theoretical maximum efficiency. And you can see in the case of silicon that it's pretty close to the theoretical maximum. But in the case of CZTS, which is what I'm going to be talking about today, it's much lower. And if we're ever going to compete with silicon, the big thing we have to change is improving the efficiency of this class of solar cells. So I'll talk about why solution process absorbers are so important here in a second. But another thing that's made this technology more challenging is the rise of lead halide perovskites, which are an amazing solution process material that have gotten these really high efficiencies. The problem is they're toxic and they're not that stable. So CZTS does have the advantage in that it's earth abundant and stable and relatively non-toxic. The problem is we have to increase the power conversion efficiency. So that's the big thing we're trying to address with CZTS. So the reason why solution processing is so important, despite this massive decrease in the price of PV, it still only represents 1% of the market. And there's decreasing investment in the capital expenditure towards building PV manufacturing plants. And the reason for that is it's a big investment for an investor to make a crystalline silicon or a cadmium telluride manufacturing plant that produces a gigawatt of PV per year. It costs $1 billion investment or $800 million investment. While the big wonderful thing about solution process solar cells, it's about an order of magnitude less expensive to make these solar cells. So this is something we really could increase the proliferation of PV because it could have a lot more investors that make these solar cells. So I want to take a quick step to the side here and talk about PV to help frame the rest of my talk and what I'm trying to do. So if I imagine the perfect solar cell, as first described by Jac Clark back in 1958, under one sun illumination, you would get 1,000 watts of light in roughly, but you'd only get 310 watts out. This is sort of a fundamental limit for a solar cell. So it's only about 31% efficient for the ideal band gap. So how we measure the efficiency of these solar cells typically is we apply a voltage when it's under light and we measure the current. This is called a JV curve. You can define what's called the short circuit current and the open circuit voltage here. We can also define an operating point, and you want to maximize the current voltage product because power is equal to voltage times current. And we can also define these two things called the fill factor, which is just the ratio of these two products, and then multiply them all together and divide by the power in to get the efficiency. So this is what I want people really to key in on here, is that there are three parameters that we're trying to maximize when improving the efficiency: the open circuit voltage, the short circuit current, and the fill factor. So what does this mean from a solid state physics perspective? If I imagine a semiconductor with a valence band and conduction band with unallowed states here, we can define a Fermi level, which is the chemical potential for electrons in the conduction band, holes in the valence band, and when we illuminate it, you get splitting of the quasi-Fermi levels. And this splitting of the quasi-Fermi levels is directly related to the open circuit voltage in a device. So this is a direct connection between the material, and I'll talk about why this is important towards connecting it to the VOC here in a second. So how does this compare for a real CZTS device, where we have this absorber layer and these other layers to help facilitate collection of carriers? So if we compare a Shockley-Queisser limit device and a real CZTS device, you can see the band structures look really different. And that's because we are trying to collect carriers in the case of the CZTS device, when the ideal one is just assumed that all carriers are perfectly collected. So a major difference between these different devices is that the fill factor, one of these key parameters, can be reduced by resistive layers in a CZTS device. Photons, in this case, is perfectly absorbed, everything above band gap, where here we have to do band bending and worry about the thickness of the film to make sure we're absorbing all the light to collect and generate carriers. There's also differences in the band edges between an ideal device and CZTS. And the big difference is, perhaps the biggest and most important difference, is how defect states can affect quasi-Fermi level splitting, which is directly related to the open circuit voltage. So taking a look at the CZTS crystal structure, let's talk about how we can get from this quasi-Fermi level splitting and connect it to defects in a material. So in CZTS, this is the crystalline structure of it. And what can happen, and what does happen in CZTS, is you have these defects that form. You have these copper vacancies and zinc on copper sites and copper interstitials. All these different defects can form, and they can form these mid-gap states in the band gap. And what happens is, when you have this population of mid-gap states in the band gap, and you have this Fermi level, you can also define a demarcation level that denotes when a defect becomes an effective recombination center, and you lose that current, basically. And what happens when you illuminate it is that demarcation level rises with the Fermi level, and it gets pinned. It pins the Fermi level from rising any further. And this is what limits the open circuit voltage in CZTS. And it turns out that a colleague of mine, Andrew Collard, looked at the intrinsic stoichiometry space of CZTS and found that for intrinsic CZTS, you don't get any quasi-Fermi level splitting. So you really have to hone in these defects so that you don't get this pinning. But even in the best case, if you compare the quasi-Fermi level splitting to the record you could get for this perfect device, you only limited to a much smaller fraction of the maximum compared to other technologies. Hey, come in. Yeah. So moving on to my first paper here, I want to talk about how the fill factor is affected in solution process CZTS devices, and what we can do to improve the fill factor for these devices. So the world record solution process CZTS device is 12.6% efficient, but uses hydrazine as a solvent, which is explosive and carcinogenic and really not something that's amenable to the scaling that we have in mind here. A solution process that we developed in the Hillhouse group uses DMSO as a solvent, which is much more benign, much more non-toxic, and is nearly as efficient as these world record devices. The problem is that when other people in the literature have tried to reproduce this, they've gotten these fine-grained layers that reduce the fill factor and the efficiency of the device. And so, during my second year of my PhD, I was having these exact same issues, and really was having a tough time advancing. What we wanted to work on was the VOC problem in CZTS. That's the meaty scientific issue, because I was stuck with low fill factors that were really ruining my device efficiencies. And it ended up that I really wanted to answer this question: of what are the physical and chemical processes that lead to these fine-grained layers that are reducing the fill factor of my device. So to do that, I want to give a brief overview of how we make these solution process CZTS films. We start with this DMSO molecular ink. We spin coat it and anneal it, and then we selenize it, where we heat it with selenium vapor. And then we fabricate devices with a number of other steps that I won't get into here, but are very important to get right. And then I'll also, throughout the talk, I'll be talking about precursor films, which represent these films before selenization, just after spin coating and annealing, and selenized films, which are after we heat them with this chalcogen vapor. So moving on to the first step, the ink in this process here, we have these different constituents in the molecular ink. We have DMSO, we have thiourea. These are complex, these Lewis basic compounds are complex with the Lewis acidic metal chlorides in solution, and acetates in some cases. And if you look at thermogravimetric analysis of the molecular ink, this is looking at the mass loss over time as you increase the temperature of the ink. If we just do a simple mass balance, we can define these different regions where the mass loss corresponds to the solvent being lost, to different impurities in the film, and then towards the CZTS itself. And you can see for temperatures up to 500 Celsius, or 525 even, you must have impurities in the film just from a simple mass balance. So this was my first indication that the fine-grained layers are related to some impurities. And so I started looking at these different anneal conditions before selenization to see how they affected the morphology after selenization. And you can see I was getting wildly different impurity layers for these different annealing conditions. So there's something interesting going on here with impurities and how they're being transported out of the film. And to answer this question, I used a technique I spent a lot of time developing. I'm going to take a quick aside to talk about that, called glow discharge optical emission spectroscopy, GDOES. And so what GDOES is a depth profiling technique where you light a plasma over a sample and you sputter away the material. This material diffuses into the plasma and emits light, which you can diffract and collect, and you have these little portions of the rainbow here. So each of these portions of the rainbow are a fingerprint for each of the different elements, basically. And this gives you some elemental signal as a function of sputtering time, basically. So this is uncalibrated data. These are arbitrarily scaled due to how complicated plasma physics is. So I use a pretty elaborate calibration procedure to make this data a little more meaningful, where I use certified reference materials, integrated the volume of sputtering, did EDX and ICP-MS, and this allowed me to find the atomic fraction as a function of depth for these different films, for both the precursor and the selenized films. This let me get a ton of data, which is really rich, and if you want the full details, you're going to have to read the paper, because I don't have any time to discuss all of this. But I'm just going to hone in on one thing related to this impurity layer. What I found was this impurity layer was rich in carbon and nitrogen in the selenized film. And so to really get at the chemical form of this carbon and nitrogen, I did another technique where I did a mechanical exfoliation of my thin film here. So you have this dense CZTS and a fine-grained CZTS, and I epoxied a second substrate on top of it. And then I lifted it off to expose this fine-grained layer, and I analyzed it with Raman spectroscopy, which is a technique that looks at the allowed phonon transitions in crystalline structures, or not crystalline in this case, and it tells you the chemical identity. Again, it's a fingerprint looking at these different wave number excitations. And what I was able to conclude from this is that these fine-grained layers are rich in amorphous carbon nitride, which comes from the decomposition of this thiourea. So you have this polymerization that's happening during the annealing process, and depending on the extent of polymerization, you can either get it out during selenization or not in some cases. And so what I found, the big takeaway from the paper, was that for this intermediate condition, you trap amorphous carbon nitride in the film. This reduces the fill factor and makes for a pretty poor device. However, for low temperature annealing conditions, you can remove the carbon and nitrogen during selenization. And for high temperature annealing conditions, you can remove it during that annealing step before the selenization. So that whole year where I was having really poor devices, I happened to be using this temperature. So that was my problem the whole time. So that's pretty much everything for the impurity transport that was in the contents of the paper. I did a lot more in this work that I don't have time to talk about, where I looked at how the alkali environment during selenization affects impurity transport, and how sulfurization is a technique to remove impurities. So I've done more with this work, and I think we've really got a much better understanding of, in these solution processes, what are the fundamental chemical and physical processes going on to help get these impurities out of the film. So with that, I want to CZTS. Again, this is this is something my colleague Andrew Collard worked on extensively. He looked at nearly the whole periodic table, trying to find things that would improve the open circuit voltage in CZTS. And he honed in on a few elements that we found interesting. There are others, but silver, germanium, and lithium were compounds that we really have interesting effects. There was something we wanted to pursue further. He left me a little bottle of silver chloride in my drawer with a little note. It was pretty great. He was like, you need to work with this. So just from a ab initio perspective, looking at DFT calculations, so if you recall back to those defects, we have a copper sitting on a zinc side or a zinc sitting on a copper side. Those all have formation energies associated with them. And in the case of CZTS, these are fairly low formation energies in many cases. A 1 on a 4 here would be a copper on a tin site, for instance. But in the case of a silver alloy device, this would be a silver on a tin site. And you can see that the formation energy of that defect is much higher. And this is due to the much larger atomic radius of silver compared to copper. If you see copper, zinc, and tin, they all roughly have the same atomic radius, so there's very little energetic penalty for them to shift around in the lattice, whereas silver and germanium have much different sizes. And so that increases their formation energy. So we really wanted to pursue this alloying strategy where we try and put in these materials, but we were having some problems. And this led us down a pathway of looking at different things, of ink chemistries, and it ended up being a paper in itself. So everything I've presented so far is the DMSO thiourea process, molecular ink, but this has some limitations. Here's some work by my colleague Andrew again, who looked at germanium chloride ink, and it completely turns into a gel whenever you add germanium chloride into DMSO. Another colleague of mine was looking at copper indium selenide, another solution process material, and found that the indium chloride had really low solubility. And so what we found was that DMF and thiourea is an amazing combination of Lewis bases that can stabilize a lot of these important compounds, particularly these alloyed CZTS compounds. So I did some work understanding what's going on with this complexation chemistry, and the deeper I dug into it, the more interesting things that I found. So if you look at just copper chloride alone in DMF, it immediately, in about the scale of 10 minutes, disproportionates into metallic copper and copper 2 chloride. But when you add the other precursors for CZTS or CIS, it stabilizes. When you add tin chloride or indium chloride, it stabilizes these solutions. So to help figure out what was going on here, I used a different source of chloride, which wasn't associated with these metals, this tetraethylammonium chloride, and I found that also stabilized the copper chloride. And after digging through the literature and looking for similar things in aqueous environments, I realized that you're forming these copper-1 complexes that stabilize copper in the 1+ oxidation state here. And you can increase the concentration and form these polyatomic complexes. So there's some really interesting chemistry going on here to stabilize the copper. And the deeper I dug into this, the more interesting things I found. I remember being online and finding the perfect paper where someone in the 90s had looked at these metal chloride complexes in DMF, and I remember going to the library and finding these figures and like photographing them, and you know, it was really interesting to go back and find these old papers that have worked on this, but there hasn't been much work on these aprotic solvents. So I was able to find that these equilibria exist for indium chloride and gallium chloride between these different chloride complexes in DMF. I also had put together how germanium chloride is stabilized as well in kind of the reverse mechanism as copper chloride. Copper chloride is stabilized by accepting chloride in solution, while germanium chloride is stabilized by giving away chloride. And this is really fortuitous because they happen to stabilize each other in the exact range we need for this alloying strategy that I'm working towards. Additionally, another interesting result we found is we were able to stabilize these selenium chloride complexes and stabilize selenium directly through the formation of these selenium polyselenides in solution. So this is all some really interesting chloride chemistry, and I was able to do a lot of interesting studies on this solution complexation using Raman spectroscopy. And again, no time to go through this data. You should read the paper though, some cool stuff. Particularly this region right here. You're looking at the vibrations in solution, and well, I'm just going to hone in on one example. So if we look at thiourea, you have this carbon-sulfur stretch right here at 744 wave numbers. And in the case of thiourea alone, you have the peak perfectly lines up with theory. But when you look at copper chloride in solution, you can see this shift in the peak. So copper chloride is coordinating with this Lewis basic site in solution, and this leads to its stabilization. So if you don't have any thiourea in solution, it's unstable, but if you, in a 2-to-1 ratio, 2 thioureas will come in complex it in solution and stabilize it. Additionally, we were able to show this with silver chloride as well. So now we have all the tools we need to do the germanium and silver coalloying, as I mentioned. So before I talk about that, I want to show one other cool thing that we did with this ink chemistry. We did something pretty novel, where instead of doing a salinization step, as I talked about earlier, we incorporated selenium directly into the ink and just heated this up. You know, instead of doing a complicated process, we did something a lot more scalable, where you just make an ink and you heat it up, and then you have an absorber. So what we did is we had copper, indium, and selenium in solution, and upon heating, this turned into copper indium selenide by itself. So this is an X-ray diffraction pattern. Again, this is the fingerprint of CIS based on the diffraction peaks from XRD. It's a fairly faceted crystalline material, and it's highly photoluminescent as well. So this is the first report of its kind. You know, just taking an ink and just heating it up in terms of CIS for making a photoluminescent solution process material that that has all of these nice properties. So that's something cool that we did. That's something cool. But to take it back to the big purpose of what we're working towards here, it was to alloy in silver and germanium, this co-alloying strategy. And now that we have the tools to do that, I want to give a little context for the work we've done with it so far. So my colleagues Jeff, Kathy, and Marcos have all worked towards trying to alloy in silver and germanium just as a follow-up work to what we've done so far. And the big thing we're trying to improve is this column right here, the VOC over the maximum VOC for this that band. And the current record was Andrew's germanium alloy device that he made a couple years ago. And recently, we got the results that the co-alloying strategy worked. We now have the highest VOC over VOC-SQ for any Kesterite device of this class that's ever been made. So really exciting results, especially since we just picked 4 compositions, sort of threw darts at a board. And I think with an optimization, we could really have the big improvement that we're hoping for here. So to summarize this work, we developed some really interesting solution chemistry. This allowed us to get this photoluminescent material without salinization. We also developed this germanium and silver stabilization mechanisms that allowed us to do this co-alloying strategy, which led to this record device. So with that, I want to shift gears to the second part of my talk, where I look at electrochemistry to address this other problem that we're facing. Like I said, the shifting landscape for PV kind of shifted where the funding is going. So it kind of facilitated me shifting towards here, but it's been a really interesting transition, and I feel like I've learned a lot in these past 9 months or so that I've been working on electrochemistry. So just to describe the problem for a second, there's imagine we have pharmaceuticals and wastewater, and we want to break them down. Well, let's imagine the perfect molecular shredder, where we find a way just to rip up these molecules, and it'd be ideal if it just worked off electricity. You just plug it in, and it'll shred up these molecules, and you would get clean drinking water out the other end. So one way we could do this is imagining an electrolytic cell, where we have electrons driving electrochemical reactions that are oxidizing these molecules. And so in the perfect case, you might be producing hydrogen gas at the cathode, and then at the anode, you're producing hydroxide radicals, or other oxidizing species that break down these pharmaceuticals. These oxidizing species would break down your pharmaceuticals, and you have some cascading oxidation pathway which just reduces them into small pieces, like acetate or something like that. So the perfect device would have 100% Faraday efficiency, which is 100% of the current that is generated goes towards the reaction of interest, basically. Which is breaking down the pharmaceuticals in this case. Additionally, we would want 100% selectivity of the oxidants towards the pharmaceuticals. So the Faraday efficiency is towards oxide generation, and the selectivity is the oxides reacting with the pharmaceuticals. In reality, though, there are many things going on in electrochemical systems. You have thermodynamics, many fundamental chemistry things, actually. You have thermodynamics. Here's the Nernst equation, where you can see the activity of the different species in solution is directly related to the Gibbs energy of whether a reaction will proceed. You have these kinetic barriers, which limit the rates of reactions in certain cases. And you also have mass transport going on, where you have the diffusion of reactants towards the surface of the electrode and products away from the surface of the electrode, and then all the bulk convective transport that we learned about a while back. So this perfect device, it's going to have all these ideal scenarios. All the current's going to go towards the oxidation. But in a real device, you have to consider all of these other effects, particularly towards selectivity towards other reactions, right? If the thermodynamics and kinetics are favorable, other reactions might proceed besides the oxidation of these pharmaceuticals. And that's exactly what happens. You have oxygen evolution, and you also have the oxidation of other species on the anode that are undesirable, the formation of these so-called TBPs, or toxic byproducts. Additionally, you can imagine how we could minimize the formation of these toxic byproducts. We want to maximize the selectivity towards these pharmaceuticals. And to do that, you want minimal dilution. You don't want it to be diluted with other waste streams, such as cooking oils and things like that, because your oxidants will be competing towards oxidizing all those other things. We just want to break down the pharmaceuticals as selectively as possible. And so we should do it where it's most concentrated, in human urine. So pharmaceuticals are excreted predominantly in human urine, and it has a fairly high conductivity and concentration of these other species. Particularly, the major constituents that we're really going to focus on are sodium chloride and urea. These are the two biggest, the highest concentration things. And you can see that the pharmaceuticals are, up to 10 millimolar, but sometimes 1 millimolar, orders of magnitude less than these urea compounds. So the question is, can we break these down when all these other things are present? So people have looked at this, and they found that there's really been a selectivity issue when you oxidize human urine. So 2 papers have looked at oxidizing stored human urine, and they found that they formed high concentrations of these toxic byproducts, chlorate and perchlorate, these chloroacetic acids and other chlorinated species. And these are at concentrations way too high, 1,000 times the drinking water limit in many cases. So this doesn't bode well for trying to oxidize urea, or oxidize urine rather, because you're going to form all these toxic byproducts that are in higher concentrations and in some cases worse than the pharmaceuticals. So how can we do better? That's what we aimed to figure out. But of these toxic byproducts, the biggest challenge is perhaps perchlorate. Perchlorate it has this cascading oxidation pathway where it goes up its oxidation chain from 3+ to 5+ to 7+. And once it's in the 7+ oxidation state in perchlorate here, it has this tetrahedral structure that's very, very stable with this massive barrier to reduction here. And this barrier, it's such a good barrier to reduction, it's commonly used in many electrochemistry experiments as a background inert electrolyte. So there is some work that's looked at electrochemical reduction of perchlorate, but you really need acidic conditions, and it's quite slow. So we're really, if we're going to do this oxidation process, we can't produce much perchlorate, or we have to come up with clever ways to reduce it, or both. So just to summarize, our engineering goal is to design devices that can control these relative rates. The rate of oxidation of these pharmaceuticals and minimize the rate of these toxic byproducts. If you just were to do some extended oxidation, you're going to generate a bunch of these toxic byproducts. But if we found a way to perhaps interdigitated electrodes, we're brainstorming some different ideas, before we got into the meat of this research. Perhaps we could somehow control these rates by flipping things back and forth, and the goal is to shred up these molecules, but without making any of these toxic byproducts. So with that, I'll move on to the actual research that we've done in this vein. So the first thing that we needed to do to actually do these experiments was to fabricate an electrochemical cell. This is something that I designed, based off Ilwan's design. But we wanted a larger surface area to volume ratio, which is important for comparing to real devices of this type. So this is what it looks like. It's made out of Teflon. It uses these planar anodes at the bottom and these rod-type cathodes at the top here. And you can imagine switching these out for different materials. This is always the working electrode in our setup here. And we have a silver chloride reference electrode that we use for experiments with our potentiostat. For galvanostatic and potentiostatic degradation. Potentiostatic degradation is when you maintain a constant voltage here, and you allow the rate of reactions or the current to change over time. And galvanostatic is where you have a constant current set at this anode, and you allow the potential to fluctuate to maintain that rate of reaction. And I'll get back to that in a little bit. We also set up this cell to be able to work with a divided setup here, using a glass frit to act as a diffusion barrier between the anode and the cathode in this case, or the cathode and the anode in this case. This is the oxidizing setup and the reducing setup. And I'll talk more about these later. But this porous frit here, this is obviously used quite frequently in electrochemistry experiments for reference electrodes. But in looking through the literature, I didn't see much about using this as a type of salt bridge to use it as a divided cell. So I wasn't quite sure if it was going to work, but it has. And I'll show you how in a second. In these different oxidizing and reducing setups, we looked at a range of different electrode materials, particularly boron-doped diamond and iridium oxide, which are used commonly in the literature. It was important to bracket our experiments with these two well-studied electrodes. We also looked at fluorine-doped tin oxide in our experiments. I haven't included that data here today because we used a thin film on glass, which is not conductive, which led to a lot of weird series resistance issues throughout the thin film of FTO. But Yuhang, my colleague, is working on making FTO on conductive substrates now. We have some promising results with FTO, so I think we can do this with a more earth-abundant material. Additionally, we looked at reducing setup, looking at molybdenum, platinum, and titanium for the reducing conditions. So yeah, this glass frit, I wanted to try something simple for a divided cell setup, and this actually proved to work really well. So zooming in at this glass frit here, if I just imagine a conductive solution, and I apply a voltage on the anode and cathode, I'm going to have the hydrogen evolution reaction and the oxygen evolution reaction. And if I look, just looking at a sodium chloride solution, you're going to have diffusion of cations towards the cathode and anions, or negative ions towards the anode. And so when I apply this voltage, I'm generating hydrogen at the anode and OH at the cathode. And what this does is it builds up a massive pH gradient. You can get up to a pH 12 in the cathode solution and down to pH 2 in the anode solution. And this is important, a little foreshadowing, because like I said, perchlorate requires these acidic conditions to break down. So we're able to establish this massive pH gradient for not that much electricity cost. It's quite cheap to do this. Scaling this up to 1.3 liters of urine, which is how much a person produces a day, is going to cost about 5 cents to create this pH gradient. So this is something that's a really powerful technique that I don't think people have used, or at least I haven't seen it. It's just an inexpensive way to swing the pH in these systems. So using these undivided and divided cells with both boron-doped diamond and iridium oxide, we looked at breaking down pharmaceuticals in these artificial human urine matrices. But we just looked at the major constituents here, urea and sodium chloride. And we found that we were able to break down cyclophosphamide, which is a particularly challenging pharmaceutical to break down. We also looked at sulfamethoxazole, which is also very common. This has been found in drinking water all across the US, and we were able to break this down as well. So using this setup, we were able to break these pharmaceuticals down on the order of 120 minutes. Additionally, in the case, if you look at the undivided and divided setup, it's pretty similar rate constants in all cases, except for the SMX, which sort of suggests that maybe these acidic environments could enhance breakdown in some oxidation pathways. So it would be interesting to follow up with more pharmaceuticals to see if there's any increase in the breakdown of these compounds. Additionally, we looked at the formation of toxic byproducts using ion chromatography over the course of these oxidation experiments. And you can see we've tracked perchlorate and chlorate. I won't get into all the data here, but the big takeaway is the chlorate and perchlorate were at much lower concentrations than what we saw from these other reports. So we were scratching our head about this for a while, and we ran a series of experiments to help figure it out. And I think we got to the root of something really interesting here. So if you look back at this paper that I mentioned before, elemental information at the stored urine solution, they measure the concentration of ammonium in the solution. And this is much lower than the concentration of the other nitrogen species, urea. The reason why they have ammonium and we have urea is that urea is rapidly broken down in the environment by biologically abundant ureas. I got really excited to put an enzyme to my talk. This urease breaks down urea and to these two ammonium. So it should be all the way up at 500 millimolar, the concentrations of these ammonium compounds if you're starting with a concentration of 250 millimolar urea. The thing is that you generate this this ammonium really quickly, on the order of 5 hours, roughly. This is looking at fresh urine stored, and looking at the pH over time, which goes up as this hydrolysis happens, and the concentration of these ammonium compounds. And what will happen is ammonium solution will vaporize and turn into ammonia gas that just leaves. If you ever cleaned out a litter box, you know exactly what I'm talking about. So these ammonia compounds, they leave, and it reduces the concentration of these dissolved nitrogen compounds in solution. And what we found is these dissolved nitrogen compounds inhibit the formation of these perchlorate and chlorate compounds. So I know there's a lot of data here. So looking at the rainbow spectrum, in the case of the orange and yellow and red, these have the full ammonium amounts in them. It doesn't matter if it's in the form of urea or dissolved ammonium. It inhibits the chlorate and perchlorate formation down to the 0.01 millimolar level. But if you have less ammonium, on the order of what Jasper and Zolli reported, you have much higher chlorate and perchlorate formation. So this is something that hasn't been reported in the literature, and it really suggests that you want to minimize, if you're trying to do these in point source treatments of pharmaceuticals in urine, you really want to do it before the ammonia leaves in these natural urease breakdown processes. So yeah, this is a cool result. But following that up with how did this affect the take a step back. So we've got this. We're generating chlorate and perchlorate in some small amount, and the question is now is can we reduce this as well? So we're generating it to some concentration. Now let's use our reducing setup that I described earlier to try and break down these toxic byproducts as well. So if we look at setting up in the reducing setup here, where the working electrode is now a cathode, and I have a test solution where we have some small concentration of chlorate and perchlorate that we're going to break down. I did a potentiostatic reduction where I held this at a range of constant voltages over time and looked at how the concentration of chlorate and perchlorate changed. And the first thing to look at is I used the starting pH of 2, which is relevant to our divided cell setup here. And you can see that for a titanium electrode, as you get up to higher potentials, the pH, it stays roughly constant from the starting pH. However, if you look at molybdenum and platinum, the pH rises, it starts to go up as you get to these higher reduction potentials. And that's because, back to the hydrogen evolution reaction, both platinum in particular has a very low kinetic barrier to the hydrogen evolution reaction. So these adsorbed surface hydrogens, they just form gas and they leave. And this slowly increases the pH over time, or not so slowly in the case of these higher voltages. And this is in competition with the reduction for chlorate and chlorate as well, where these adsorbed hydrogens reduce the adsorbed chlorate and perchlorate on the surface. So just looking at the different rate constants here, you can see, for molybdenum, for chlorate, for example, you can see the rate goes down, and this is due to the competition of these two reactions. So we haven't explored this space very much. As I mentioned before, electrochemistry, there's so much with the selectivity and the kinetic barriers. Electrode choice really matters. But as a first step, we were able to show that you can reduce chlorate and perchlorate at pretty reasonable rates, as I'll show you in a second. So let's combine these concepts, right? Let's imagine taking this galvanostatic oxidation treatment of a pharmaceutical solution, and we oxidize it, lower the pH here, and then we put that low pH solution into a reducing setup here with a cathode that can be used to break down these pharmaceuticals, but at a low enough potential so you don't have hydrogen evolution. So you have an acidic environment, you're not generating hydrogen that stays at low pH, and we tracked the toxic byproducts over time. So we have this oxidation treatment for 2 hours, and then a long time reduction treatment, where this is at minus 800 millivolts on titanium, and here we just did the oxidation treatment that you saw previously. And what we've shown, this is sort of a proof of principle, but both the perchlorate here and the chlorate were reduced to maybe 70% and 50% of their starting value after oxidation here. So this is a really cool proof of concept, something people haven't explored, where it's all electrochemistry, all electricity, just clever ways of flipping divided cells using these divided cell setup. And we're reducing the chlorate and perchlorate. Additionally, in the ion chromatography data, there were peaks that are yet unidentified, and we're reducing these byproducts as well. So this suggests that, right now we've designed this to focus on chlorate and perchlorate, but we could use this scheme to reduce all sorts of toxic byproducts as well. You could imagine using a combination of cathodes to do these reductions. So I think these are really interesting, like a proof of concept for this scheme. So to that end, we recently filed a patent where we patented different ways of doing this to actually make a device that goes in place at a urinal. You can imagine we would start with places like a hospital urinal or something like that, where you expect a very high concentration of these pharmaceuticals to reduce the load that's actually going to the wastewater treatment facility. And it's really simple. I got to make a process flow diagram, which I haven't done in a while. You have this divided cell setup. You oxidize, you get low pH of the pharmaceuticals, feed that into the cathodic chamber, where you maintain a low voltage. And you can imagine the urine that comes in here is split 90-10, and the anodic and cathodic compartments. And then you recycle to break down the pharmaceuticals that happen to get split on this side. And you could cycle this a few times, each time reducing the pharmaceuticals more and more, until you send it off to the wastewater treatment facility. We've also brainstormed a few other ways to recycle this hydrogen gas, to incorporate that with the reduction as well. There's some literature showing that you can use hydrogen gas on catalytic surfaces to reduce perchlorate as well. So we could have some high surface area catalytic material that helps the breakdown of perchlorate. So really interesting concepts here. So to wrap it all back up, we had this goal of making a clean energy device, turning sunlight into clean energy. And so I've worked on this technology of solution process CCTS, helped understand these physical and chemical processes going to reducing these fine-grained layers that were hurting the fill factor in the films. And we also got a new record for this Shockley-Quasar limit VOC. And this is a really promising result that I want to hear how it goes over the years. Also, we've worked on this device to break down pharmaceuticals in contaminated wastewater and using that to make clean water. And we've got this really cool device design, which I look forward to see how Yuhong and the rest of the group continue to advance this technology and see where the patented work goes. And so maybe one day, if everything goes well, we'll have a CCTS solar cell that's powering a molecular shredder, having clean energy, doing our work to clean up the pharmaceuticals as well. So with that, I want to thank so many people. Wow, yeah, it's been, there's so many people to thank. My lab mates, I'm so grateful to have worked with you over the years. Anna, thank you for coming. Anna flew out here for this defense. It was so great. Yeah, Dr. Hillas, thank you so much for your advice and mentoring over the years. Thank you to my committee for being here. Brian, thanks everyone who helped practice this. Thank you, my family, for visiting. And everyone else, Ashley, Shiraz, Rachel, I can't name everybody, but thank you so much. And with that, happy to take any questions.
Questions for Jack?
Great talk.
Thanks.
So I have a question about fouling. It seems like urine would be a pretty gnarly solution to make your cathode and anode be happy for very long. Did you investigate this at all, or do you have thoughts about?
So we've kicked around a few ideas to this end. It is something we need to test, particularly on the cathode. You're worried about polymerization reactions, and it would be nice if we could have anodes and cathodes that we've talked about alternating. So if it's been at a reducing environment, somehow switching them to an oxidizing to blast off anything and then go back. But this is part of the technological development, right? We have to see what the challenges are in order to face them. And so far, we haven't seen any issues like that. But in real systems, you're right. I mean, maybe there would be more of these issues.
Yeah, and just a quick follow-up. Like, what would the consequences be as fouling builds up on these? Do you think? Like, would you start to see more perchlorate? Would certain?
I don't think you would start to see more perchlorate. I think what you would see is the effective area of your electrode going down. And so, if you're trying to pass the same amount of current, that means much higher voltage, which can facilitate other reactions and maybe enhance perchlorate formation. But I think in these devices, the picture is just putting on a constant voltage. And if you just have a constant voltage and you're slowly reducing your electrode area, it's just going to decrease the rate of reactions, basically. It's going to make them less effective towards pushing these reactions forward.
Such a great talk. I have a question about your theoretical perfect molecular shredder. So I know that you did a couple of pharmaceuticals in the cell that you created. Could you use any pharmaceutical to do? And would it break down in that way, or do you think that there are certain pharmaceuticals where you would need to do something different?
That's a good question. Yuhong, how many pharmaceuticals do you have in the lab now? Maybe 7 or 8?
Almost 10.
Yeah, so we're thinking about that for sure. We chose two that are kind of on a spectrum here. SMX is pretty easy to break down. It breaks down with these so-called active chlorine species that are homogeneous in the solution. They're generated at fairly high concentrations in these matrices. And it's fairly easy to break down. Like I said, very commonly studied in the literature. Cyclophosphamide, on the other hand, is not studied that well, but it's very challenging to break down. We've been working with another professor, Mike Dodd. We asked him, what's the most challenging pharmaceutical that we can prove that we can break down? He's like, probably cyclophosphamide. So he's been doing this research for a while, and so I think that's a really good candidate for one of the most challenging things to break down. But we have some other ones like carbamazepine that we really want to take a look at and see if we can break down those as well.
Given that for your solar cell research, that you use earth-abundant materials and that will be cheaper compared to the silicon ones, what percentage efficiency do you think you have to get to be competitive with silicon? Because theoretically you might not have to get to the same efficiency, right? If it is cheaper per unit area to print them. Mm-hmm. So what do you think you have to get up to?
I remember Dr. Hillis telling me back in 2014, if we made a 15% device, it would change the world, and it would be a game changer. I think that's probably like 17, 18% now. It's creeping up on us for sure. I think 15% would be amazing. It would revitalize the field of CCTS for sure if we did that. But to really make an impact, I think we're going to have to start getting closer to 20%. So, the solution processed PV isn't realized yet. It's still theoretical, but it's interesting enough. The scalability of that technology is interesting enough that I think it is worth pursuing, and it's I think 18% to answer your question, something along those lines. Andrew?
For your pharmaceutical stuff, so you're oxidizing these pharmaceuticals to break them down and then reducing toxic byproducts. Is there any chance that in the reducing step you're like regenerating the pharmaceuticals?
That's a cool question. I think that may be possible. Like in very particular cases, if I imagined I just chlorinated a pharmaceutical and then I somehow just put a hydrogen back on it, you could say, okay, you oxidized it, put that chlorine on it, and you took it off. But in reality, it's way more complicated than that. If you look at, I've done a little bit of literature review on the mechanisms of the breakdown of these pharmaceuticals, and what happens is you have one of these radical species. They attack a carbon bond, and this just cascades and just chews it up. I mean, so it's a matter of entropy, where it's a very low entropic state to have 1 millimole of a very particular chemical structure, and then if you're just switching it back and forth, or you're just blasting it with all these oxidants, it's usually the breakdown products are so far removed from the pharmaceutical themselves. It'd be like a hurricane putting a house together if it were to pass back through or something like that.
You used silver and germanium
I did.
to improve the. Do you know exactly what those dopants are doing? I mean, are they passivating some defect?
Yeah, man, I have multiple backup slides on this. I think. Oh man.
He says.
Yeah. Thanks for the planted question. There are so much interesting literature about silver and germanium alloying. I think germanium alloying is kind of understudied for this field, given that it has the highest VOC review of CSQ made in our lab. But just little bits of silver, like 10% alloying, 5% alloying, you can see a 50% increase in the carrier lifetime just with 5% silver alloying from TRPL data here. You can see that there's this carrier freeze-out issue when you look at the temperature versus efficiency for just measuring PV under different temperatures, and this freeze-out issue somehow disappears when you just have 10% alloying in there. So this suggests just small amounts of silver alloying really change what's going on in the material. And then you combine this with another material that's been shown to improve the open circuit voltage. I think there's a real chance that you're going to have beneficial effects in the same for different directions using this covalent strategy.
Other questions for Jack? Okay. Well, let's thank Jack once again.